Hello everyone. So today we will discuss the nucleophilic substitution reactions. So nucleophilic substitution reactions, or we call it SN reactions, where S stands for substitution and N stands for nucleophile. So when I discuss SN reactions, I classify it into two categories. That is, there are two types of SN reactions, SN1 and SN2. Now what do we mean by 1 and 2? 1 and 2 means that these are your unimolecular reactions, and SN2 means that these are your nucleophilic substitution and the reactions are bimolecular. So 1 stands for unimolecular and 2 stands for bimolecular reactions. Bimolecular reactions. So let us discuss it one by one. So let us start with SN2. Now SN2, as the name suggests, it is nucleophilic substitution bimolecular. Nucleophilic substitution bimolecular. Now what do we mean by bimolecular? It means that if I start with a substrate molecule, suppose I have methyl chloride. Suppose I have methyl chloride, and I am talking about the hydrolysis of this methyl chloride in the presence of, for say, aqueous KOH. Then this OH will act as a nucleophile and it will replace Cl, and I will end up getting methyl alcohol. Plus I have Cl minus, which is a leaving group, and OH minus is your adding nucleophile. So bimolecular means that the rate of this reaction depends upon the concentration of both, that is substrate molecule methyl chloride as well as the attacking nucleophile. So rate is directly proportional to the concentration of substrate and the nucleophile. Hence, I can call this SN2 reaction that it follows second order kinetics. It follows second order kinetics. Now let us see some of the features of this SN2. Now, number 1. So suppose if I start with a chiral substrate molecule, suppose I have a chiral substrate. Molecule. For say I have this. This is how can I, suppose I have this bromoalkane. And what I am doing is, I have OH minus, or say from KOH, this is your attacking nucleophile. Then what happens in SN2? In SN2, first of all, SN2 is your single step process. It's a single step reaction. When I say single step reaction, that means when this OH minus comes and attacks this substrate molecule. Now, so depending upon the type of aliphatic alkyl halide, whether this carbon is sterically hindered or it can be like 1 degree. So what do I mean by that? If this carbon, like for example, if I have smaller groups here like X, Y and Z, and if I have a 1 degree carbon. 1 degree carbon means that this carbon, which is attached to this bromine, is attached to just one carbon, that is your 1 degree. So if this is sterically not hindered, then what happens, this OH minus, it tend to attack this substrate molecule from the back side. That means this incoming nucleophile, it tend to attack from the back side. So basically I can show it like this, this tend to attack from the back side. Now what happens, this results in the formation of a transition state like this. I have carbon, this, this is my transition state, this is my transition state. Now the carbon is basically shown with 5 bonds, so this is your transition state which is unstable. This is your transition state and this is unstable. So what happens in the transition state, that this is your concerted mechanism, single step reaction, and it follows concerted mechanism. Concerted mechanism means that when this transition state forms, here we have the simultaneous bond breaking and bond forming. So this bond is getting formed and this bond is breaking. So we have a simultaneous bond formation and bond breaking, and what happens next is that we have a bond, we have alcohol that is formed, and this Br leaves, and this is how I can show it. We have OH attached here, this, and this is how I can show it. So if you see carefully, I started with some configuration, and when I get the product, there is an inverse in the configuration, because Br was leaving from the front side and the incoming nucleophile is attaching from the back side. So I am calling it inversion in configuration. Inversion in configuration. Inversion in configuration. Now, this is also called Walden inversion, and this is 100% inversion. 100% inversion. This is also called Walden inversion. Now, what does this inversion means? That if my substrate molecule is having R configuration, then the product will have S configuration. Hence, I have 100% inversion in the product. So if I have a chiral substrate molecule, I end up getting inversion, 100% inversion in the product. Now, other features of SN2. So since I told you that here we have a transition state that is being formed, and this transition state is unstable for obvious reasons, because carbon is shown with 5 bonds. Now, there is no intermediate formation. This is very important point. There is no intermediate formation. There is no intermediate formation. And these reactions usually are favored in the presence of, and these reactions are favored in polar aprotic solvents. Polar aprotic solvents. What do we mean by polar aprotic solvents? That the solvents are polar, we have polar solvents, but they do not have, for say, OH and NH, right? So, for example, we have acetone. We can take acetone. We can have alkane nitrile, for say methane nitrile, CS3CN. We can have dimethyl formamide like this, and then dimethyl formamide. And we can have dimethyl sulfoxide. This is also called DMSO. This is our DMF. We can have methane nitrile, and we can have acetone. So these reactions are favored in polar aprotic solvents. Now, if I discuss the stability order. Now, in the beginning, I told you that if this carbon is not sterically hindered, then SN2 reactions are usually favored. Why? Because you know that OH minus is attacking from the back side. So if this carbon is already sterically hindered, then there would be no space for this incoming nucleophile to attack. So for example, if I say stability order, if I give you that if I have CS3Cl, CS3CH2Cl, or we can have CS3CH, CS3Cl, or CS3C, CS3Cl, then if you see carefully, this is your 2 degree, this is your 3 degree, and this is your 1 degree, right? So if you see these three, then I can easily say that the order of SN2 or the reactivity of SN2 reactions, then this is more reactive than 2 degree, and finally with 3 degree, because 3 degree carbon is sterically hindered. And if you compare these two, then it is clearly visible that we have a longer hydrocarbon chain and we have a shorter hydrocarbon chain, and this is even more sterically less sterically hindered. So CS3Cl followed by CS3CH2Cl, then we have a 2 degree carbon, 2 degree alkyl halide, and then we have a 3 degree alkyl halide. So this is the stability order, or we can say reactivity order. We can say reactivity order, that this one is most reactive among these 4. Now, when we discuss SN1 reactions, so as the name suggests, SN1 means nucleophilic substitution unimolecular. Now, what happens? First of all, this is your two-step reaction. There is a formation of an intermediate. There is a formation of an intermediate, and we will see that this intermediate is your carbocation. Then these reactions, they follow, since they are unimolecular, that the rate is only dependent upon the concentration of the substrate molecule and not on the concentration of the nucleophile. And so this is a two-step reaction. There is a formation of an intermediate. Rate is directly proportional or dependent upon the concentration of substrate, and we can also say that it follows first order kinetics. And these reactions are favored in polar protic solvents. For example, we have water, methanol, we can have ethanol, right, etc. We can have formic acid, acetic acid, and so on and so forth. Now, and suppose if I start with a chiral substrate molecule, like this, then what happens? Basically, this is, since I told you that this is a two-step process, step number 1 is basically your leaving of this halogen group. You know that halogens are good leaving groups. So in the first step, this halogen leaves. Now when it leaves, you know that initially in the substrate molecule, this carbon is sp3 hybridized. So we have sp3 hybridization. When I say sp3 hybridization, that means the geometry is tetrahedral. Now once this Br leaves, I end up getting this carbocation. And this carbon is sp2 hybridized. And when I say sp2 hybridized, that means that this is your planar. Structure. I started with the tetrahedral geometry, but now I get planar structure. And please note that this is your slow step, that the rate is dependent upon this step only. Now, what happens in the next step? In the next step, I have this carbocation. Now, since I told you that this is your planar structure, then the incoming nucleophile can attack either from the front side or from the back side, or from the above or from below. So, what I'm saying is, incoming nucleophile is having two-way two paths to attack this. Now, this is your front side attack and this is your back side attack. But please note, now if this is the case, then can I say that I will end up getting 50% inverted product or 50% retention product? Or I can also say that if it is 50-50, then I can also call it, then there will be a racemization. Yes, that there is the formation of a racemic mixture. But my question to you is that is it 100% racemization? Is it 100% racemization? 100% racemization means that is it 50% inversion and 50% retention? Then my answer to this question is that no, this is not 100% racemization. This is partial racemization. We have partial racemization. Partial racemization with inverted product more than the retention product. For example, if I say this is 60% and this is 40%, this is hypothetical. Now, why this happens? Let us see. So we know that this is your carbocation and this is my incoming nucleophile. Now you know that this reaction is taking place in some vessel, right? So we have the solvent, polar protic solvent, and the halogen which leaves this substrate molecule is there in the reaction mixture only. So first say we have this halogen here only in the reaction mixture. So what happens? We have the plus sign on this carbon, we have negative on this halogen. Can I say that there are some sort of attractions? Yes or no? There are some sort of attractions. There are some sort of attractions. Yes? And because of these attractions, what happened? The front side attack is somehow hindered. The front side attack is somehow hindered. And the back side attack is, the back side is free. Yes? So, the back side attack is more favorable than the front side attack. Now, the question, you might have a question that if it is, there are some forces of attractions between this carbocation and the halogen ion or this anion, then why this front side attack is there? Like, why isn't it 100% backside attack? Now, what made this attack somehow facile? So the answer to this question is polar protic solvent. Now, what happens in the presence of polar protic solvent? I have this anion. This anion undergoes solvolysis, or if it is water, we call it hydrolysis. So what happens? We have water like this. Right? We have water like this. So what happens? The water molecules, what happens? That this anion is surrounded by the water molecules, and I say that this anion will undergo solvolysis. Now what happens because of this solvolysis process? What happens? Basically, the attractions, here I have the carbocation. So what happens? The attractions are somehow weakened. Why? These forces are somehow weakened. Why? Because the water molecules have come and sit in this space. So we have lot of water molecules which surrounds this anion, and hence they weaken these interactions. Now, if these interactions are weakened, then we can say that front side attack is somehow facile. And front side attack is possible, though it is not possible with what we call equal probability as compared to the backside attack. But yes, we have front side attack which is somehow possible. Why? Because of the solvolysis of anion, and this is the reason why these reactions are favored in the presence of polar protic solvents. Right? So somehow facile means yes, there is there is hindrance, there is what we say, these water molecules act as an obstacle, that this is not a what we call 100% facile attack, but yes, the attractions are somehow weakened and hence front side attack is somehow possible. So what we have is that after in the step number two, when I get this carbocation, what happens? This incoming nucleophile can attack from both the sides, and I have both type of product, inverted plus retention. Yes, inverted product is somehow more than the retention product. So it is not 100% racemization. This is partial racemization. We call it, this is your partial racemization. Partial racemization. Now, one more thing, if I discuss the reactivity order, now since reactivity, now it was clearly seen that this reaction is this proceeds by the formation of this intermediate carbocation. So, and you know that 3-degree carbocation is more stable. Why? Right? 3-degree carbocation is more stable than 2 degrees. So, can I say 3-degree alkyl halides are more reactive for SN1 than we have 2 degree, than we have 1 degree? Yes or no? And also, if I ask you a question that what type of mechanism this benzyl chloride undergoes. So basically, you know that after the removal of this chlorine, once this chlorine leaves, I end up getting this carbocation, which is a stable benzyl carbocation. So if there is a possibility of getting a stable carbocation, and you know benzyl carbocation is very stable because of this delocalization it is stable by what we call resonance, right? This is your resonance is stabilized, and hence this undergoes SN1 type of reaction. Yes, I hope this is clear. Yes, one more thing, that suppose if I have something of this sort, then and suppose if I have Cl over here, and if I ask you what type of mechanism it follows. So if I talk about that this carbon is attached to 3 other carbons, so SN2 is ruled out, right? SN2 is ruled out. And if I remove this, when this chlorine leaves, I end up getting a carbocation like this. And this positive is on the bridgehead carbon. This is your bridgehead carbon. And carbocation at this position is unstable. Why? Because this is so strained position that it cannot be a planar structure. And you know carbocation is planar in nature. So this is according to the Britt's rule, that carbocation is unstable at bridgehead carbon. Right? So SN1 is also ruled out. So this is how it goes. I hope you understood the topic. Thank you so very much.